Am I audible to you all?
Yes, sir.
Yes, sir.
Okay, fine. So let us start with
Yes.
this chapter
Yeah.
number 29. Yes, anybody anything want to convey? Okay, so we'll start with this new chapter, that is chapter 29. So today by evening, I'll be sending you the notes, the slides on this chapter 28 over your group mail. So please collect it, go through it, and even if you are still having any doubt in that chapter number 29, sorry 28, then I am still open to you all to clarify your doubt. Is there anything you want to clarify or you want to ask anything? Any doubt? Okay, not only concerned to chapter 28, but anything. Okay, fine. So let us start with this chapter number 29. So as I was talking in the last class towards the end, that in our day-to-day life, even though the with the modernization of technology, we have started using more and more DC instruments and components, but still then AC is still popular. Now, if I will tell you or I will ask you what is a power system, okay, please listen to me carefully. If I will ask somebody what do you mean by a power system? So power system means it must have something to generate electrical power. Usually the hydropower plants, the thermal power plants, the nuclear power plants, your let us say your photovoltaic arrays, all these comes under your generating system. Now, usually what happens, these generating systems are located quite far away from the cities or from the urban settlements, because we purposefully used to construct these generating system or generating plants away from settlements. It is because they are always dangerous to the common man or common mass. If we are having a nuclear power plant, you very well know that they are quite dangerous. One example was the Chernobyl disaster in the year 1982. And during that time, because of some miscalculation in a testing process, the Chernobyl incident took place. They have actually bypassed a number of safety mechanisms in order to test, and the testing was done by some inexperienced engineers. Even though they are very good engineers, but they were quite young to carry out such a testing, and all of a sudden, the reactor went out of control because they have withdrawn some control rods, and because of that, this incident took place. That time it was Soviet Union, communist country, and over there during those times they tried to hide this incident from the entire world. But finally it was detected, and by that time a lot of people have lost their lives, and generation fell into the trap of this disaster. So that was why I am talking about this. It is because the town of Chernobyl, or the town was built around that nuclear power plant, which was housing all the engineer staff of that nuclear power plant. So it is always dangerous to have normal settlement near to power plants. So naturally, even your hydropower plant, though it seems to be nothing wrong in that, no sort of danger situation, but still then, just imagine if the dam collapses, there will be flash flooding and people will lose their life. Similar is the case with thermal power plants. So thermal power plants, if the boiler or means burst, naturally it is going to be dangerous for the general mass. So in this way, we can say that your generating plants should usually be located far away from cities and villages, urban areas. Now, if they are located far away, maybe the ideal distance is 100 and 200 kilometers away. So if this is the case, then power is generated somewhere and the power is consumed somewhere. Usually we generate the power in hydropower plant located in the valleys, in among the hills, and usually the settlement is in plain areas, and maybe the distance is around 300 kilometers. Now, this is the reason why we usually keep the generating plants far away from normal people settlement. Now, just imagine if instead of generating AC power, they would have generated DC power. Then the problem is that when you are transporting this DC power over this 300 kilometers through transmission lines, and transmission lines are nothing but conductors having some resistance of their own. Maybe the modern conductors they are having 0.02 ohms per kilometer, and just imagine if it is a 100-kilometer line, then obviously the ohm means the resistance is 2 ohms. Now 2 ohms seems to be a very small resistance for a conductor line, but just remember, if I am transporting around 1000 ampere of current, the voltage drop in the line will be 2000 volt. So if you are generating 11 kV DC, you at the home you will get a nine, at the settlement you will get a 900 volt, sorry 800 volt DC, or sorry 9 kilovolt, 9000 volt. So there will be a drop of 2000 volt. So this is going to create a lot of losses. For that reason only, the major reason behind using the AC is that AC can be increased to a higher value at a very low cost, and that too in a very simple manner by using this transformer. So the transformer is also going to make use of this electromagnetic induction technology in order to step up the voltage from 11 kV to maybe around 200 kV or 132 kV, something like that. So once the voltage is increasing, the current is going to decrease. So in this way, that is the major reason why we always prefer AC for generation, transmission and distribution. And utilization, I told you that usually nowadays with the development in technology, we are using this DC signals. But before that, if you see, all the utilization part was also operating on DC, on AC. Fans till now in your college also, if you will visit, you will see all the fans are your normal fans working on AC. The air conditioners, if 70% of the air conditioners used nowadays are still non-inverter type. That means they are using pure AC signal to run the air conditioners. Even in your house, you are having water pump, your refrigerator, all of them are still working on AC signal. Now, if you want a DC, then it is very easy to convert this AC signal to DC signal just by using either two diodes or by means of four diodes by using a diode bridge. You will install on, you will require four number of diodes, one capacitor and a transformer. Even if you are not having a transformer, doesn't matter, by using a resistance and capacitor you can still step down the voltage to a lower value. So in this way, getting a DC from AC is quite a simple task, and it is very economical. But the reverse is always a very costly affair. Why? Because either I told you in the last class, if you are going for a 1 kilowatt rectifier, it will cost you maximum it will cost you 2000 rupees. If you will make it by your yourself, it will hardly cost you 500 or 600 rupees. I have developed many rectifiers for the use of my house because I have a passion for electronics and I used to do some experiments. Therefore, I required DC signal. For that, I used to make my own rectifiers, and hardly they cost me 500 rupees. But at the same time, if I will go for an inverter of 1 kilowatt, at least I have to cough of around 5000 rupees or more than that. Around 10 times I have to spend, and the circuit is going to be quite a complicated one. And the most important thing is that from a AC signal, you can get a fairly good DC signal. But from a DC signal, you cannot get a very good, accurate sinusoidal AC signal. It is quite difficult. For those purposes, we always prefer the generation, transmission, distribution, and to some extent the utilization to be in AC signal. Okay. So this is why I have told you the differences between your AC usage and your DC usage, and why we are always preferring this AC. Now, well and good. Till now, up till this chapter, we have studied about DC signals, and I have told you there are multiple number of ways we can generate DC signal. The most common one you have been studying from the school is by using cells where or batteries where you are having some chemical reaction taking place, and that chemical reaction is producing a steady current or a steady voltage signal. Similarly, nowadays we are also having PVRs where the sunlight will fall on a particular cell made out of silicon dioxide, and because of that it is going to generate electricity, and that electricity is a DC signal. Similarly, you have your fuel cells, you have your turbine means that piezo thermic applications where you are getting DC signal. Okay, that is a different aspect. Now onwards from this chapter 29, we will see how this AC is actually generated. What is the principle behind this AC generation? So in order to generate AC, the only or the best possible way is by making use of electromagnetic induction. Okay, when we are talking about DC signal, over there I told you that in the case of batteries, we may go for some chemical reaction, and that is going to generate this DC signal. Well and good. So that is one process. The other process is by using your photovoltaic cell. The neutrons in the sunlight is going to just knock out one of the electrons from the valence cell of this silicon dioxide, and it is going to form a DC signal. Well and good. That is a different way to produce DC. Similarly, for your piezoelectric generators, you maintain two different temperatures for two electrodes, and because of the difference in the temperature, so one of the electrons will move out and it is making a DC signal. So this is a third way of producing a DC. The fourth way is by application of thermocouples. You maintain two different, yes, you maintain two different electrodes at different temperature. You are going to get a DC signal. So in case of DC, there are multiple number of ways by which you can get a DC signal. But in case of AC, the only and the best possible way to generate is only one. That is by electromagnetic induction. So now we will have to study what do we mean by this electromagnetic induction, what are the immense salient features of that, and how actually we can design a very simple AC generator. Okay, so let us move on. So in order to understand the concept of electromagnetic induction, the most important thing that we need to understand is your magnetic flux. No doubt we have already studied it, but since we are going to make exhaustive use of this magnetic flux in this particular chapter, therefore let us have a recap of that. So I have already told you what is a magnetic flux. So it is nothing but the magnetic field lines passing through a area held perpendicularly to the field lines. What does that mean? Are all the field lines going to be perfectly perpendicular to the unit area or the area? No, it is not possible, because 90% of the magnetic flux are always non-uniform. So if that is the case, then how we can generalize the mathematical expression for this magnetic flux? So we have already studied about that. Once again I am telling. So if I am having a, let us consider a uniform magnetic field. So this is a uniform magnetic field, but the problem is that it is inclined to the surface over which we want to determine the magnetic flux. So for that, what we have to do? We have to first draw the unit vector of the surface itself. So the unit vector for this surface is pointed upwards in the black arrow. Now obviously this one, this magnetic flux B vector is making some angle with respect to this unit vector of the area. Now, as I told you, only the perpendicular component of this magnetic flux is actually going to contribute to the magnetic flux. So what we have to do, since it is inclined, we will decompose it into its horizontal and vertical components. So by doing that, I am getting something B perpendicular. And if we will mathematically see, this B perpendicular is nothing but B cos phi. And remember, here we are not interested for the orientation of phi because this is a cos term. Okay. So cos of phi is same as cos of minus phi. That's nice. So over here, ultimately we can say the magnetic flux through this surface is nothing but the perpendicular component of your B vector, sorry, the component of the B vector perpendicular to the surface. So in this, mathematically we come to the conclusion it is nothing but B cos phi dA. Now, obviously, your B is a vector quantity, area is a vector quantity. So, if we will write it in a little bit modified manner, it looks like B vector dot dA vector. Now, this is d phi. Now, we are not interested for differential flux, we are interested for the total flux. So, for that, we have to integrate it. So, once we integrate it, what we are getting is phi B is equal to integration of B vector dot dA vector, which is nothing but in terms of magnitude, it can be written as integration of B dA cos phi, or we can write it as B cos phi dA. This is known as the generalized expression for magnetic flux. What do we mean by generalized expression? That means it can be equally applicable for both a uniform magnetic field as well as a non-uniform magnetic field. Number one. Number two, this can also be applied to any type of surface, whether it is a flat surface or it is a curved surface, doesn't matter. If it is a surface and if it is a magnetic field, then we need to apply this generalized expression in order to find the magnetic flux through that area. So I hope everything is very clear to you all, or is there any doubt? Yes? Okay, I will proceed further.
Yes, sir.
Okay. Why I am telling? Because please have this idea of this magnetic flux very clear. Okay. Now let us move on to Faraday's law of induction states. Okay. Now, what does this Faraday's law of induction states? The definition is very simple. Don't go by this definition. Just look at the mathematical formula. It says that the EMF induced because of this electromagnetic induction E is equal to the negative of the change in the magnetic flux, because phi B is magnetic flux and d phi B by dt is nothing but the change in magnetic flux. So what is the stuff about? What is the change in magnetic flux? Now just have a look. So just look over here. Here I am having a coil. Look to this diagram first. Here I am having a coil. So if this coil is made out of, let us say, copper wire, doesn't matter whether it is copper wire or iron wire or aluminum wire, it doesn't matter. If it is a conductor, it is well and good. But usually we prefer this copper conductors because they have a good conductivity, that means they have low resistance. Secondly, they can handle very high temperatures, because electrical engineers, they know that when current or any generator is loaded, current starts flowing in the windings, and more the winding, more the current, more will be the temperature produced in these windings. So your conductor must be able to handle these types of heating. Therefore, usually we prefer this copper because it satisfies the condition of low resistance as well as high thermal capacity. But please make it clear, this can be any conductor, aluminum, nichrome, it can be iron, it can be silver, it can be gold, doesn't matter. But in practice, we make use of copper wires. Okay. So now, in a very simple way, let us try to understand how actually this entire procedure is actually taking place. So here I am having a coil, and this coil obviously will have two ends. So these two ends are connected to a galvanometer. So what is a galvanometer? A galvanometer is an instrument which is going to detect if there is any production of voltage or any current is going to flow. It can detect both of them. And the best part is that it can detect in both direction. Positive, we can measure current, or it can detect current flowing in clockwise direction as well as anti-clockwise direction. And thereby it will give the deflection either to the left or to the right. So this is the best thing about this galvanometer. Okay, so here I have connected a galvanometer. Fine. Now what I will do, suppose let us say this magnet, let us consider a permanent magnet which is made out of a bar magnet. So this is a magnet, and this is the north pole, let us say, this is the south pole, let us say. You know, if I am having a magnet like this, then obviously the magnetic field lines are going to move out from the north pole. So this is the magnetic field lines which are going to form the magnetic flux. So these things we have already understood. Now the magnet is not moving, that means it is stationary in nature. So if it is stationary in nature, then the magnetic field lines that are cutting or passing through this coil is also stationary. That means over here, whatever was the magnetic flux, at one time after 10 minutes also the same magnetic line is passing through it. So there is absolutely no change in the flux linked with this particular coil. Now, when I will start moving this magnet into this through the central axis of this coil, what is going to happen? You can see the fluxes will start cutting this one. Previously, this flux, this particular line was passing through this coil or this turn. Once it has moved inside, it will pass through this one. That means over here the change in the linkage or passing of the flux started. That means each of the coil, or sorry, each of the turns of this coil is now encountering a different value of flux as the coil, as the magnet is moving. So, in other words, I can say there is a change in the magnetic flux linked to each of the turns of the coil. Now, I have told you that the coils are nothing but single turns, all of them connected in series. So, naturally, what will happen? The entire voltage will be created, and there will be a voltage drop across this one, across the galvanometer. And the galvanometer is a device which can measure both voltage and current. And as you can see, this is a closed circuit. So as I started moving this magnet into the center of this coil, the fluxes started changing. So once the fluxes started changing, there is actually a generation of EMF in the coil or across the two ends of the coil. So if that is the case, then we can very easily formulate or say the Faraday's laws of electromagnetic induction says that the induced EMF, here we usually don't say it as simple EMF, we rather say induced EMF because we are actually inducing it. So the induced EMF E is equal to minus d phi by dt. Now, one confusion is still arising. But why for this minus is there? Okay, wait for some time. When we will study about this Lenz law, over there I will tell you what is this, why it is say minus over here. For that you have to wait. So at least we come to the conclusion that if the magnet is stationary or the magnet and coil both are stationary, then obviously the fluxes passing through or cutting or linking these turns of the coil is fixed. So there is no change in the flux linkage, therefore E is equal to 0 because d phi b by dt is equal to 0. Now when the magnet starts moving or the coil starts moving or both of them starts moving relative to each other, then obviously what is going to happen? There is a change in the magnetic flux linking or passing through the coil. Therefore, as per your Faraday's laws of electromagnetic induction, there will be a generation of voltage. So this is the best thing. So as I told you that when the North Pole is actually moving in this direction, what is going to happen? The galvanometer is actually pointing towards the right direction. Well and good. This is your right direction. This is your zero position and this is your left position. So it is going to direct towards the right hand side. Now, when this magnet, it has entered into this, now let us take it outside. So once I will start moving this magnet outside, slowly what will happen? Yes, anybody? Any idea? Yes, nobody. What is happening?
So flux will change.
Yes,
The flux will change.
flux is going to change. So what will happen to the pointer of the galvanometer? Yes.
Sir, it changes. It changes the direction of current.
Do you think it will change the
Means the
direction?
pointer
Actually,
will.
over here it is something wrong is given. That's why I am telling. Okay. Now look over here. Okay, so here we are having the zero position. Here we are having the, let us say it is 10 volt in this direction, and here it is 10 volt in the other direction. So this is the 0 volt position. Now when I start moving this magnet inside this with the north pole aiming towards the coil, slowly what will happen? Your voltage coil will be, or the pointer will be over here. Now when I will recede it outside, what is happening? The flux is reducing. So this one will start reducing and it will move towards this zero position. Whereas over here it is given in the other direction. So this is the wrong thing that I want to point it out. Now, let us do one thing. Let us reverse it. Suppose this is the south pole and this is your north pole, and let us do the same thing. That means let us insert it into the coil. So if I do that, you will see that the pointer is not pointing in the right direction, but it started increasing and it reached the maximum position in the left direction. Similarly, when I will take this magnet out of it, that means I will take the south pole away from this coil, then you will see that slowly this pointer is moving towards the zero position. So this is how the entire setup is going to work, or this is the basic principle behind the generation of electricity in this world. Got it? Yes? Anyone who has any sort of doubt? So this is a very simple setup, and this simple setup is actually generating a AC voltage. If I am going to alternatively change the or reverse the direction of the north and south pole, if I am not going to do that, it is actually producing a pulsating DC. So forget about that. At least we come to the conclusion that if the magnet is moving with respect to the coil, or the coil is moving with respect to the magnet, or both of them are moving with respect to each other but having a relative motion, then obviously there will be a generation of EMF as per your Faraday's law of electromagnetic induction. Now, why I am talking about this relative motion? Let us consider this case. I am having a coil. Okay, this coil is connected to a voltmeter over here. Well and good. And here I am having a magnet. Now, suppose let us say this magnet is moving at 10 meter per second towards this coil. And if the coil is stationary, then the relative speed between both of them is 10 meter per second. So there will be generation of EMF. Now let us consider the reverse case. The magnet is stationary, the coil is moving towards the magnet, and let us say it is moving at a speed, a constant speed of 10 meter per second. In this case also, there is a relative motion between the magnet and the coil, and therefore an EMF will be generated. Now just think, the coil is moving in the direction in this manner and the magnet is moving in this manner, both of them are moving at 10 meter per second, so the relative motion is 20 meter per second, again there will be generation of EMF. But now let us do one thing. This coil is moving in this direction, the magnet is moving in the same direction, and both of them are moving at 10 meter per second. So the relative motion is zero. So if the relative motion is zero, no EMF is going to be generated because the flux is constant even in this case. So please remember all these important things. Maybe in the exam, I may ask you a question. A magnet is moving from left to right. The coil is also moving from left to right. Both of them are moving at 10 meter per second. So what is the EMF that is going to be generated? The EMF will be double. The EMF will be half of the actual generation. No EMF will be generated. The correct answer is no EMF is generated. Got it? Everybody clear about the concept?
Yes, sir.
Okay. Okay. So finally what we learned? That magnetic flux is actually not the cause of induced EMF. So it is not the magnetic flux which is actually going to create the induced EMF. But induced EMF are only caused when there is a change in the flux. If the flux through a circuit has a constant value, whether positive, whether negative or zero, there will be never any induced EMF. Okay. So usually when I was talking, I have actually given the formula as E is equal to minus d phi b by dt. Remember, this is only for a coil having one single turn. So if I am having a n number of turns, then the equation is a little bit modified. We just multiplied a n over here because I told you a coil is nothing but having a number of turns in series. And in case of series, you know the voltage gets added up. So since all the turns are identical, therefore I just multiplied n over here. Nothing big deal about that. Both of the equations are correct. The first equation is the law of Faraday, and no doubt it is only considered because it is meant for a single turn coil. But usually we never go for a single turn coil because the voltage will be very feeble. For that reason, we go for a coil having n number of identical turns. Please remember identical turns. So if that is the case, then your Faraday's law is modified a little bit and is written as E is equal to minus n times d phi b by dt. Okay. Now, till now we have been talking about this magnitude part. So magnitude of the voltage, okay, fine, we got that E is equal to minus d phi b by dt. So once we know the change in the flux, then obviously we simply have to multiply with minus n and we will get the value of the EMF generated. But EMFs also have a direction. Now this is a confusing thing. Now current has a direction, okay, current has a direction, but we have studied that it is not a vector quantity, and the direction of current means either it is flowing in the clockwise direction or anti-clockwise direction or from top to bottom or from bottom to top, something like that. Now when I will tell you the direction of induced EMF, what does that mean? That means do this EMFs also have direction? No, actually they don't have direction because your EMF is also a phasor quantity. It doesn't have a direction like your vectors, but it do have some direction. Now you are also conversant with the direction. How? In case of EMFs, the direction of a EMF is nothing but the polarity of the two ends of the source. For example, in a battery, we have a terminal, positive terminal, the other one is a negative terminal. Now, In case of AC, if you could remember in the demo class, I have told you, in case of DC, we have the direction as plus and minus. But in case of AC, we have something known as phase and neutral, P and N, or line and neutral, both of same thing. Now you will go to just take out a plug from the socket and you will see on one side, particularly on the right hand side, you will see that something L is written, and on the left hand side of the two pin you will see N is written. L stands for line, N stands for neutral, and the top it is earth. So forget about this earth. We are actually, when we talk about the direction of induced EMF, we actually mean which one is positive with respect to the other one. So this is known as the direction of induced EMF, or we can say the direction of induced EMF is actually referring to the polarity of the conductor ends, which is behaving like a EMF source. For example, suppose I have a coil, the same coil that we have been discussing right now. So this is a coil, and when the magnet is passing through it, one of the end is going to be at higher potential with respect to the other one. So in this case, rather than writing P and N, we usually take it as plus and this as minus. Now when the magnet moves away and the other pole enters, this becomes minus. Suppose the north pole is entering and is moving to and fro. So this one will be plus, this one will be minus. Now if I am using the south pole over here and moving this magnet to and fro, then this is going to be negative and this one is going to be positive. So this is known as the direction of the induced EMF, or this is known as the polarity of the induced EMF. Now, determining the direction of the induced EMF, or determining the direction, means polarity of the induced EMF, is a little bit tricky method. Okay. So what I will do is that, of course, I have written a note on this. I will explain it, no doubt. But before that, I have some clipping in my video. Please go through it. Over there, actually, I have used my own, my hand, my fingers, my thumb in order to explain it. So over now, I'll be playing a very short video, a very small portion from the long video, and please go through it for some time. Actually, it will take 10 to 15 minutes because the video itself is around 1 hour. But I will just start it at 9 at the time 9 second, 9 minute, and it is going to end at 26 minutes. So from this portion of 17 minutes, you can actually learn what do we mean and how we are actually going to determine the polarity of the induced EMF. Is it okay? Are you ready?
Yes, sir.
Only single voice, no
Yes, sir.
chorus.
Yes, sir.
Okay, but remember, today's lab class is not like I will just play the video, you will watch it, maybe seriously, may not be seriously. No, this is not possible today because time is running out. We have to be very serious because we have to complete the course well within the time. And for that, I am obviously I can explain it, no doubt. But I felt that by seeing that video, you will get a better idea. And once you gain that idea, I will again play these slides and make you understand. Twice I will be teaching you regarding the direction because it is very much complicated in the book. In the book, if you go line by line, take your own time, even as a teacher, it is very difficult on my part to understand. So please go through the video, it will be beneficial for you. So right now what I will do is that I have to change the setting of the audio. So my voice will not be audible to you, neither your voice will be audible to me. You just keep on watching. At the right time I will close the video and I will change the settings so that we can interact. Is it okay?
Okay, sir.
Shall we start?
Yes, sir.
Yes? Okay, fine.
Yes, sir. Yes, sir.
Okay, okay. Please be serious in seeing that video. Huh? You're all. This is chapter number 3. It is at this position, and when I will basically machines, electrical machines, be a magnet. What I cited over here, one single number of turn. Now, the production or a will come to try to find what is the direction of the EMF induced, because finding the direction of EMF induced is of utmost importance to us. And when we are talking about direction of induced EMF, we are actually, because that EMF or E or voltage is not a vector quantity. It is obviously a phasor quantity. But when we are talking about direction of induced EMF, we are actually interested to know the polarity of the coil or polarity of the source of induced EMF. So direction of induced EMF. So there is a particular procedure. Obviously, there are two ways by which we can find the direction of induced EMF. So one by one, we will try to describe both the methods. So the first method that we will be adapting in order to ascertain the direction of induced EMF has a number of steps. So the first step is to, okay, before that let me tell you that suppose the very, for simplicity, I am having a very simple coil, simple circuit which is consisting of a single coil, and let us say here I have connected a load. Now in the book you will see that the load is not drawn over here. Why I have drawn it? Because otherwise it is basically going to be a short circuit. So basically your coil is from this point to this point. So this is the conductor of the loop, conductor of the coil, and this is the load. So in total you can say this is a closed circuit. Now the first step is to draw the area vector of the loop. First we have to draw the area vector of the loop. Now if this is the loop and it is present on, let us say, XY plane, then I can say that its area vector is directed in this manner. Now let us say, suppose I have a magnet over here. Now this is the north pole, and let us say this is the south pole, and let us say this magnet is moving towards the coil, and when it is moving, obviously the magnetic field lines are moving like this. These are the magnetic field lines, as you can see. Here it is entering into the south pole, and from the north pole it is emerging out. Now obviously when it is moving, the magnet is moving towards the coil, then obviously there will be a change in the flux associated or linked to the closed circuit. And when this is going to happen, obviously an EMF will be generated. Now we are supposed to find the direction of the induced EMF. So as I told you, when I am going to find the direction of the induced EMF, I am actually talking about the polarity. So I have to find ascertain which one is positive and which one is negative out of these two terminals. So how to do that? Now, for that, the first step is to find or draw the area vector of the loop. So area vector of this loop is in this manner. Second thing, here we have to take something into consideration or assumption, step 2. So here what we have to do? Here we have to tell that if north pole is approaching, when north pole is approaching, then we'll consider the flux to be positive.
phi B is positive. Similarly, if south pole is approaching, then we will consider your phi B is negative. So this is quite important. Next, third, when the pole moves towards when the magnet moves towards the coil, then your change of flux is considered to be increasing, or rather I will say it is positive. Okay, so when magnet, I'm not talking about the poles, I'm talking about the entire magnet. It doesn't mean whether this is north or south. When magnet approaches 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 the coil or the loop, then your d phi b by dt is considered positive. Okay. Similarly, when magnet moves away from loop, then your d phi b, that is the change of flux linked to the coil, is considered as negative. Okay. Now this is the final step, step number 4, and this step number 4 will help you to find the direction of the induced EMF, or rather I will say the polarity of the induced EMF. So how to do that? Now the first thing is that we have to use right hand thumbs rule. Right hand thumbs rule. Now what we are going to do? Your thumb should be along positive area vector. That means in this case, this is my right hand, and the thumb, as you can see, is along the positive A vector. Okay. And secondly, as you can see, suppose let us say the loop is on this paper, then obviously your A vector is directed upwards. Towards the, as you can see, I have pointed this pen upwards. So this pen is in along the direction of A positive A vector. Now I have to curl my fingers. When I am curling my fingers are in anti-clockwise direction. So my fingers are in anti-clockwise direction, and it is in this direction of the loop. So curled fingers are anti-clockwise in this direction, counterclockwise in this particular case. Now, how to ascertain whether E is going to be positive or negative? Always remember that if now in the third sub-step, we have to apply this formula. E is equal to minus d phi b by dt. Now, if your E is positive or E is greater than 0, then E is positive. In this case, always remember that your direction of E vector, direction of, sorry, not E is not a vector quantity, direction of E is along the direction of curled fingers, is along the direction of curled fingers. That means your E is going to be in this direction. Okay, curled fingers, and vice versa. If your E is less than 0, then E is negative. That is direction of E opposite to curled fingers. Okay. So when we have learned these steps, then we are now in a position to apply. This principle in order to find the direction of the polarity of the induced EMF. So here I will be telling all the conditions, all the cases. So the first case, let us discuss. Case 1. So what is the first case? Okay. So case 1. So case 1 is, suppose I am having a loop over here. Here I have connected a load. So this is the loop. The loop has a area vector, A vector in this direction. Okay. Now, suppose let us say a magnet is approaching or a magnetic field is approaching the North Pole is approaching this coil and it is trying to enter. So in this case, as you can see, your B vector is in this manner. So here in step 2, I have told you if North Pole is approaching, then phi B is positive. So the first thing is that since the North Pole is approaching towards this coil, therefore I will write phi B is positive. Is positive. That means the value of phi B is phi B. It is not negative phi B. Second step. Second step is whether your d phi B by dt is positive or negative, that we have to ascertain. Obviously, it is going to be positive because in the third step I have written when magnet approaches the loop, then d phi B by dt is positive. So in this case, it is going to be positive because your magnet is approaching towards the loop. So in this case, your d phi B by dt is also positive. Okay, now we have to apply the right hand thumbs rule. As you can see, my thumb is pointing in the direction of A vector, and if I start curling my fingers of the right hand, you will see that the direction of my fingers is in this way. The direction of my fingers is in this way. Okay. Now we have to find the value of E. So we have to use that expression E is equal to minus phi by dt. Now since phi B is positive, so your d phi by dt is also positive. Okay. So minus of positive d phi by dt is going to be a negative term. So in this case, E is negative. E is negative means over here I have told you if E is less than 0, that is negative, then the direction of E is opposite to the direction of curled fingers. That means the direction of your E or induced EMF is in this manner. If this is the case, then obviously this is going to be positive and this is going to be a negative. Okay. Second case, case 2. Now in the same way, suppose let us say this is the same coil. This is your A vector. Now the same magnet has, which has previously in the case 1 was entering, is now moving away. Now when it is moving away, what are the changes that we have to find out? Now in this case, first, similarly we have to ascertain the direction. So first is whether phi B is positive or negative. Obviously phi B is positive because North Pole is towards this loop. Secondly, what about this d phi B by dt? It is going to be negative because in step number 3 I have told you when the magnet moves away from the loop, d phi by dt is considered as negative. So I will write minus d phi B by dt. Okay. Third, we have to apply the right hand thumbs rule, and obviously my fingers will be curled in this direction. Right? So in this case, next for the fourth step, E is equal to minus of the change in the flux, and the change in the flux d phi by dt is going to be negative. So this negative and this negative makes it to be positive. So it is becomes d phi by B by dt, and this E is positive. So if E is positive, now go to step number 4, sub-step number 4. Now here I have written E is greater than 0, E is positive, direction of E is along the direction of the curled fingers. That means the direction of your E will be along the direction of your curled fingers. Now if this is the case, then obviously this terminal is going to be positive and this terminal is going to be negative. Okay. So in this way, in the previous case, this was positive and this was negative because your E was negative. If E was negative, it is against the direction of the curled fingers, and therefore this is positive and this is going to be negative. Similarly, in the case when the magnet is moving away, then in this case your E is calculated to be positive, and therefore your direction of induced EMF is along the direction of the fingers. So in this case the polarity sign of the source or the loop changes. So this becomes positive and this becomes negative. Next, case 3. So in this case, let us do the same thing, except that here the south pole is approaching. South pole is approaching. Again, the same way, this is your A vector. Now, in this case, what is the changes? Now, first thing, your phi B is negative. That means it is minus phi B. As I told you that if south pole is approaching, phi B is negative. So since south pole is approaching, so phi B is negative. That is minus phi B. Next, your d phi by dt, d phi b by dt is positive. Why it is positive? Because a magnet is approaching or moving towards the coil. So in this case, this is positive. Now, if this is positive, then obviously if I will put minus d phi in place of this phi b, then obviously I am going to get a minus d phi b by dt. Okay. Next, putting our right hand thumbs rule, the fingers are again directed in this way. Simple. Next, we have to find E. So E is equal to minus or negative of minus d phi b by dt. So in this case, it again becomes d phi b by dt, and therefore E is positive. So if E is positive, then it should be along the direction of the curved finger. So this is my E. Obviously, this point becomes positive and this point becomes negative. Now the last case, case 4. Now in this case, the same way, this is the loop with the load. Obviously in the book you will not find this load. It is only saying that this is a coil, but I have drawn this load in order to tell that this is not a short circuit. Okay. So as I told you in many times, I have told you the definition of a short circuit, that if the source is not connected to through any load, the two terminals of the source is not connected through any load, then it is considered as a short circuit. So here I have connected a load over here. Okay. Now let us come back. So this is again your A vector. Now the south pole, the magnet with the south pole and the north pole is moving away. Okay. So if this one is moving away, what is going to happen? Now the first thing, your phi B is negative as usual, because the south pole is near to the coil. So it is minus phi B. Next, d phi b by dt is negative. Why it is negative? Because the magnet is moving away from the coil. So in this case, this is going to be minus d, and here this is also minus. So minus d phi b by dt. So ultimately this becomes d phi b by dt. Okay. So minus turns out to be d phi b by dt. Next, put our right hand thumbs rule. So in this case, the fingers again in this direction. Okay. Now E is equal to minus or negative of the change of flux with respect to time. So this one is minus d phi b by dt, and therefore E is negative. So if E is negative, then the direction of induced EMF is going to be opposite to the direction of your fingers, curved fingers. Therefore, this is going to be negative and this is going to be positive. So in this way, we can easily find the direction of the induced EMF. Okay, now we'll talk about generator. So what is basically a generator? As I have told you beforehand, that generator is an electrical machine that converts mechanical energy into electrical energy by utilizing the principle of electromagnetic induction. So basically here we will be talking about
Am I audible?
Yes, sir.
Yes, sir.
Okay, have you gone through that video? Yes, everybody? Anyone please respond?
Yes, sir.
Let us do one thing. Let us
Yes.
have a break for 15 minutes. We'll resume our class at 3:20, and for the next 40 minutes, I will once again explain how we are going to find the polarity, because my experience in the last year, students were very confused, and therefore I have taken special care to explain it, not only in by the video but also in the slides. Then we'll talk about this Lange law, and after that we will move on for motional electromagnetic force, EMF, motional EMF and induced EMF. We will talk about two different things. So this is a case of motional EMF. So in case of motional EMF, we will talk about two types of generator. One is a isolated moving generator. This is a hypothetical generator. Again, we will talk about a rod connected over a stationary U-shaped conductor. So this is again a hypothetical one, because the real practical one are not to be taught in this syllabus. Next, we will move on for this. This is actually a Maxwell's equation, one of those Maxwell's equation. Next, we'll study about this induced electric field, and we'll stop the class over there. But remember, today we have to complete quite a lot of stuff. So within this 40 minutes, we'll try to complete it. So let us have a break for 15 minutes. So it is 3:07. So we'll start at 3:20. Okay, go and refresh yourself, and by 3:20, please be online. Okay, you remain online, but physically you come over to the screen. Okay.
Yes, sir.
Okay.
Yes, sir.
Okay. Go and have a break. Are you all online?
Yes, sir.
Okay. So it is
Yes, sir.
3:30. So we can start. Okay, Ashish, we'll start. Okay. So no doubt in the video you have understood the procedure. Now again I am telling you because last year
सर
I had, yes,
सर एक पूछना था एक बात सर
sure.
ये फोर साइज पेपर अगर सर नहीं होगा तो रोलिंग कॉपी में सर लिख कर देने से होगा असाइनमेंट
हाँ बेटा उसमें I don't think there is any problem. Now let me tell you actually we are actually not checking the assignment copies. The work has been outsourced to the section coordinators and they are actually checking the copies, and I don't think that will be an issue at all. I don't think you can definitely write it in a rolling copy, no problem for that. Okay.
ओके सर थैंक यू सर
Okay. So let us start our discussion. So basically, I was telling that whenever we are having a coil or we are having a loop, let us in this example, let us consider a simple case of a single turn coil, or which we usually call it as a loop. And over here I have made a little modification. Now the modification is that over here I have connected a resistance. Okay, now the purpose of connecting this resistance is to ensure that this entire thing does not becomes a short circuit. Okay, no doubt it will generate an EMF, but the first thing is that you cannot ascertain what is the polarity because there is no end points. In the book, if you will see, okay, let me show you the book. Let us see it in the book. So here I am having the soft copy of this book. So here is the soft copy, and in the book, okay, everything is given. Now over here, you are having a disc, okay, or rather I will say a single turn coil or a simple loop. But here the problem is that there is no positive or negative terminal. Why? Because this is a loop and moreover it doesn't have a terminal. And it is quite very uneasy for not only the student but also for the teacher to explain. The reason is every source is definitely going to have two number of terminals. If it is a AC source, phase neutral; if it is a DC source, positive negative. And in this example it has just taken a ring. So in that way, you cannot say that this is going to be an EMF source. Secondly, if at all anywhere we will point out that okay, this is the leftmost corner is the positive terminal and the rightmost corner is the negative terminal, but still then there is some problem. The problem is over here we are seeing that the entire disk is made or entire loop is made out of a conductor, and whenever there is an absence of any load connected to the conductor, it is actually a short circuit. Okay, so remember what is a short circuit. There is a source, and if the two terminals of the source are connected directly through a low resistance path like your conductor, then it is going to be a short circuit. So always remember that only when there is some load connected to a source through the conductor, it is actually termed as a circuit. Okay, if there is no load, the two ends of the conductor or the EMF source is connected through a conductor of very low resistance, then obviously it is a short circuit. For that reason only I have made some modification. Okay, now let us consider this case where I am having a loop, or rather I will say a coil of a single turn. So it starts from this positive terminal, ends at the negative terminal. So this particular loop is actually your EMF source, and to this EMF source I have simply connected a resistance, because here I am connected a load. Now we all know that whenever a magnet is going to approach towards this particular loop, then obviously there is a change in the magnetic flux linked to this coil or to this loop. Therefore, an EMF will be generated. Now, obviously, an EMF will be generated. Its magnitude you people could easily calculate, but the problem is now we have to ascertain what is the polarity of the loop, or in other words, what is the direction of the induced EMF. So let us try to find out. For that, we have to consider some features or some statements. The first one, flux is considered positive if and only if the north pole is facing the coil. Got it? The flux will be considered positive only when the north pole is facing the loop. So over here in this case, so I have considered four number of cases. Case one is north pole is approaching towards this loop. Okay, so naturally the flux which we will take for the calculation is considered to be positive. That is phi b is greater than 0. First statement. Second statement, whenever a magnet, whether doesn't matter whether it is the north pole or the south pole, doesn't matter. Whenever the magnet is actually moving towards this coil or this loop, then remember that your d phi by dt is considered greater than 0 or positive. That means in this case, as you can see, your magnet as a whole is approaching towards this coil. Okay, moving towards the coil. Therefore, the change in the flux linked to the coil is considered positive. Now, with these two statements, let us now put the relationship E is equal to minus d phi b by dt. Okay, so over here, your phi b is positive. So I put positive phi b d by dt. Well and good. This is also positive. So if this one is positive and there is a minus sign outside, so that minus sign gets over here, and as you can see, your E is equal to minus d phi by dt. This one is positive, d phi by dt as a whole is positive. So a positive quantity with a negative sign is nothing but is going to be less than 0. Therefore, I can say that the EMF induced when the north pole is approaching the loop is considered to be negative. Negative means, what does it mean? And how to ascertain the polarity? Just do one thing. So if this is the loop, first draw the unit area vector. Now, unit area vector over here can have two directions. One like this, the other one towards the bottom. We will not take the bottom one. Why? Because as per our rule that you have seen in the video, that it is the unit vector is the one on the side from where the magnet is actually approaching or receding. So the moment of magnet is on the upper half of this loop. Therefore, I will consider the unit vector of the area to be pointed in this direction. So if that is the case, now I will use my right hand thumb rule. What does this right hand thumb rule says? My finger will be along, sorry, my thumb will be along the direction of your A vector. So over here in the figure, you are seeing a thumb, and the thumb is pointed towards the direction of this A vector. Whereas the four fingers of the right hand is curled in the anti-clockwise direction. Okay. Now, just go through this line. Direction of the induced EMF is opposite to the curled fingers. Why? Because E is negative. Okay. Your curled fingers are always in the direction, and if the EMF is negative, then the polarity over here will be plus and this one will be minus. Is there any doubt? Is there any doubt over here? Either tell a yes or a no. Anybody having any sort of doubt, please tell me.
No, sir.
Please be frank, doesn't matter, because last time I have been telling this particular thing a number of times. Students can't understand it. So if you are still having any doubt, please tell me. I will explain it a number of times. Doesn't matter, but you should understand it properly. Are you sure everything is okay? You got this idea? Hey, can you hear me or not? Hello? Somebody
Yes, sir.
please. Okay. Whenever I am asking anything, at least one of you please respond, because sometimes it may so happen that I may be out of connection. So in that way, it's quite a inconvenience. Okay. So this part is over. So North Pole is approaching towards the loop, number one. Since North Pole is facing the loop, phi b is considered positive. First point. Second point, the magnet is approaching towards the loop. That means d phi by dt is positive. Two things have been ascertained. Now put the Faraday's law of electromagnetic induction. E is equal to minus d phi by dt. Phi b is positive, so d phi by dt is going to be positive. And moreover, it is also determined that d phi by dt is positive. So this negative sign, if multiplied, results in E to be a negative quantity. If E is a negative quantity, then the direction of this induced EMF is opposite to the direction of the curled fingers. What does that mean? That means this one is positive and this one is going to be negative. Next case. Okay, North Pole has approached and now it is receding or moving away from the loop. So what are the changes? Let us try to find out. Flux is considered positive. Yes, of course it will be positive, because North Pole is still facing this loop, or the loop is still facing the North Pole of the magnet. Therefore your phi b is greater than 0. Next, the change in flux is going to be negative. Why? Because it is moving, the magnet as a whole is moving away from the loop. So in this case, your d phi by dt is less than 0, or it is negative. Now let us put these two facts over here in this equation. So we will put it. Now phi b is positive, well and good, we have put phi b. But this as a whole is going to be negative because the magnet is receding away from the loop. So minus over here. This within the bracket, again there is a minus sign over here. So minus over here. So minus becomes plus. So E becomes positive. If E becomes positive, then remember the direction of the induced EMF is along the direction of the four curled fingers of your right hand. So the polarity will be plus over here and minus over here. Got it? Got it, or is there any doubt? Somebody please respond.
Yes, sir.
Yes? Okay. Next. Now let us consider the case of a south pole. So here I am having a magnet, but in this case the south pole is actually facing this coil. So if it is facing the coil, the first thing, the flux is negative. So phi b is less than 0 or negative. The magnet as a whole is approaching the loop. So d phi by dt is going to be positive. Okay, we have made it positive. Now these two facts have been ascertained. Let us put it in this equation. Over here, d phi by dt. Now in place of phi b, I will put minus phi b because south pole is facing the loop. So here I have put minus phi b. Secondly, this as a whole is going to be positive because the magnet is approaching. Now there is a minus sign over here, so minus sign is left over here. So minus minus it becomes plus, or your E is positive. So if E is positive means it is in the same direction as that of your curled fingers. So again it will be plus and minus over here. Previous case the same thing was happening. The E and the curled fingers both were in the same direction, therefore the polarity was plus and minus over here. Now once the magnet with the south pole has moved towards the loop, now it will recede. So when it is receding, number one, phi b is less than 0, d phi by dt is again less than 0, because it is receding, that means it is negative. Now when these two are negative, put it in this equation. So this over here it is minus phi b. This as a whole is again minus with a minus sign ahead of it. So this total becomes negative. So that means the direction of the induced EMF is against the direction of your curled fingers. So the polarity once again becomes plus and minus. Is it okay for you all? Everybody understood this thing? Or is there any doubt? Please ask me. If everybody ever understood, then no doubt it is a very nice thing, because last year I had to face a lot of problem. Students were still having doubt. Okay, that's good. Now let us move on to another law related with this direction of induced EMF. This Lenz law. Now, Lenz law is not a mathematical law. It is a method or another law which is used to determine the direction of the induced EMF, but over here it is actually based on some important fact known as the conservation of energy. So we will use that method in order to ascertain the direction of the magnetic electromagnetic induction, or rather I will say the induced EMF. Now, okay, rather than going for this, we will go back to the same diagram once again, but before that let us see what does this Lenz law is actually saying. So Lenz law is an alternate method for determining the direction of induced current or EMF. Okay. So if there is induced EMF and it is a closed circuit and induced current is going to flow. Well and good. Lenz law is not an independent principle. It is actually derived from Faraday's law. We'll see that negative sign is actually because of this Lenz law. Lenz law states that the direction of any magnetic induction effect is such as to oppose the cause of the effect. Direction of induced currents as a bar magnet moves along the axis of the conducting loop. Forget about this line. We will most likely to discuss this line in broad term. We'll discuss after some time, but let us see how this one is used to in order to determine the direction of the induced EMF. Now let us move back to this diagram. Now can anybody tell me in the source how the current is going to flow? Whether the current in this loop is going to flow clockwise or anti-clockwise. Anyone? Yes? Who will tell me? Come on, tell me. Hey, no, not a single one can answer it. Now just see. From here, from this plus to this minus, this portion is actually an EMF source, and this is a resistance, that is the load. Now my question is, in which direction the induced current is going to flow, or forget about the induced current, the current is going to flow in the EMF source. Yes, think about it. Now this diagram can also be thought in another way. Suppose, let us say, I will say that this is the EMF source, this is the positive terminal, and this is the negative terminal, and to this we have actually connected this load. This is the equivalent one. Now tell me in which direction the current is actually flowing inside the EMF source. Not a single one.
Sir, negative to positive.
From?
Negative to positive inside the battery.
Excellent. From negative to positive. Very simple. I don't know why you people are taking so much time. Now, whenever we have talked about the direction of current, we have actually considered that the current is flowing through the load. Now, obviously, current flows from higher potential to a lower potential inside the load. So, over here, the current is actually going to move from this end of the resistance to this end of the resistance. Now, if the current is flowing from positive terminal of the load to the negative terminal of the load, then inside this EMF source, which is nothing but a coil or a turn, how it is going to flow? It is going to flow in the anti-clockwise direction. Now, if it is going to flow in the anti-clockwise direction, then in which direction do you think the magnetic field is going to be created? Why? Because I have told you, no doubt this is creating a magnetic field. This one is responsible because this magnet itself is having a magnetic field, let us say B. This B is creating this flux phi BM, phi B. And when this is moving, it is creating d phi B by dt. And this is going to create an induced EMF. Just see the sequence. Look at the chronology. Now this is going to create the induced EMF. The induced EMF is actually going to circulate the current I because the load is connected. And this current I is again going to produce a magnetic field because we know that whenever current flows in a conductor and EMF is magnetic field is generated, and this is nothing but a conductor. Coil is made out of a conductor, and therefore because of the flow of this current in this coil, we will be having a magnetic field, and that magnetic field is known as your induced magnetic field. Now this induced magnetic field is, if we will keep our means apply right hand thumb rule, then we will see that this magnetic field is actually going to be in this direction. Is going to be in this direction. So your B, which was created because of the permanent magnet, is in this direction, whereas the B induced because of the current flowing in the circuit is in the opposite direction. That means, which clearly states that if you are trying to move this magnet into the coil, you will face some resistance. You will face some resistance. For example, it is previously these types of things we are doing in the laboratory, but nowadays we are not doing because the course has changed. Now suppose there is a magnet over here, and in that experiment what we were doing, we were simply connecting to this to a galvanometer. So when we are connecting this coil to a galvanometer and we are pushing this magnet into this, it was moving very smoothly. So there will be a thread, this thread will be actually on this side, and the students are asked to pull it, and when they will pull it at a high speed, then you will see that there will be deflection. Next, what we used to do, we used to disconnect this galvanometer and connect a resistive load like a bulb, like a small flashlight bulb. And when at that time we ask the students to pull this one, when they will start pulling, they will say that, sir, something is preventing me from pulling this one. So who is preventing? Is it a ghost? No, it is not a ghost. It is the induced EMF, because in the previous case there was no load. It was actually an open circuit because the galvanometer is having a very high resistance. So it was almost like an open circuit. So very limited amount of current was flowing. But now we have replaced this galvanometer by means of a load. So when there is a load, there is a flow of current. It is a closed circuit. So when you will start pulling it, the current, or rather I will say induced current, is going to flow. This induced current itself is going to produce a magnetic field. And this magnetic field is known as the induced magnetic field. And this induced magnetic field will always try to oppose the cause of its magnetic field. That means a child is born and it is trying to kill his or her mother. Okay, the effect is always trying to oppose the cause. So this is known as your Lenz law. Another important thing, if you want, or you people might have ever experienced, whenever you are going to start a diesel generator, they tell that always disconnect the load and start the generator. Reason, if you are pulling that recoil, then you will feel very easy to pull it if it is not loaded. But if it is loaded, you try to pull it, you cannot pull it. It is very difficult, because once you start pulling, EMF will be start generating. This will circulate a current in the circuits through the loads, and this current is again going to produce a induced magnetic field, which is going to oppose the magnet. So this is the reason, or this is known as your Lenz law. Are you understanding what I'm saying? Yes? Or is there any doubt, anything you want to ask? Yes?
So here the plus and minus symbol are written for the resistor or the loop. I think this
Or
is
the
for
register. Or the register. Now you let me tell you why I have written it for the load. Always remember that whenever we are going to give any polarity to any source, we are actually not giving the polarity to the source, rather for the load we are giving. We are giving the polarity symbol to the source, taking into consideration that it will be connected to a load. Okay. Yes?
Yes.
Anything else?
No, sir.
Shall I move further? Shall I move further or not? Okay. So this is all about your Lenz law. Okay. So these are the various ways by which we are achieving this change in flux. So here there is a coil, and here is a magnet. If we will move this magnet, then you are going to get a change in flux, and an EMF will be generated. Next we have the magnet is stationary, the coil is moving. Again there is relative motion, and there will be EMF induced. And if both of them are moving with respect to each other at a relative speed, then, or there is a relative motion between both of them, then obviously they are going to produce an EMF. Now, I have knowingly kept this paper blank because I want to explain this Lenz law once again to you all. Okay, so now I told that your Lenz law says that because of some reason, or this is the cause and this is your effect. Now, what is the cause of EMF in case of a generator? First one, change in flux. Now, how change in flux is achieved? Because there is a magnetic field. So this magnetic field, when moves, it is going to create a change in the flux, because every magnet is associated, whether it is an electromagnet or a permanent magnet, doesn't matter, it is associated with the electric field, and whenever it starts moving, it will lead to a change in the flux. So because of this magnetic field or movement of this magnetic field, I am getting a change in the flux. Now this change in the flux is going to produce or induce an EMF. So this way I am going towards the effect. This is the cause side, this is the effect side. Now if that coil or that loop is connected to some load, obviously it is a closed circuit. So a current will be induced, or an induced current will start flowing. Now this induced current, what it will do? Actually the induced current is also flowing through or passing through the conductors of the generator. In case of a battery, that was not a problem because it was not a conductor. A battery, there were chemicals, there were some electrodes, and both of them were actually not going to create a magnetic field. But over here we are using a coil, and over here coil is made out of conductors, and that is the reason why the current when flows through this conductor is going to create a magnetic field. So the ultimate effect is this, and moreover this current is changing. Okay, if this current is changing, then it is also going to change, or it is going to create a magnetic field which is actually changing. So this is the induced flux, and this, or rather we'll not talk about this, rather we'll say this induced current is going to produce this induced magnetic field. Now what happens? So the ultimately I can say this is the main cause and this is the main effect of the entire process. Okay. Now the problem is that this effect, you will be opposing this cause. That means if this B is directed in this manner, suppose it's having some magnitude, let us say 5 Tesla, and it is in this direction, but your B induced will definitely be directed in this opposite direction. But whatever the magnitude will always be less than that of this B. If it is more than that, then obviously your B cannot move, your magnet, permanent magnet cannot move. If it cannot move, then obviously there will be no such thing. So let us say this one is going to have a strength less than or equal, not less than or less than, and very much equal to that of your 5 Tesla, but never equal to 5 Tesla. Okay. So in this way, whatever is the main cause, it is having a main effect, and that main effect is actually opposing this main cause. You got it? Is there any doubt?
No, sir.
Okay, thank you. Now let us move on. So by now we have been talking about EMF. So first 5 to 7 chapters we studied about this EMF, but that was concerned only with DC. Next, we started studying about this EMF because of this change in the magnetic flux. Now, there are actually two types of AC EMF source, or rather I will say EMF by which are produced by electromagnetic induction are actually of two types. One is a motional EMF, the other one is a induced EMF. Not a very big deal. Now, one example of motional EMF is all the generators which are producing AC voltage. All the generators. Another or the other one is your induced EMF. So one example of induced EMF are all the transformers that you are seeing, whether it is a small transformer inside an SMPS circuit or it is a very big transformer in the substation. Now, in both the cases, the principle of Faraday's electromagnetic induction is exactly the same. It is equally applicable in the it means it is equally applicable to both of them. But the thing is that in one case it is known as motional EMF, the other one it is known as induced EMF. Now, what is the major difference between them? Now always remember that motional EMF is means it is because that whenever there is a motion of a conductor inside a magnetic field, there will be a change in the flux, and whenever there is a change in flux, it leads to the generation of this EMF. So that is because of this motion, it is known as motional EMF or motional electromagnetic force. Whereas a very simple thing, let me tell you. Suppose, let us say, I am having a coil. I am having a coil. So previously I was passing only DC current and therefore I was getting a steady flux. Now let us say I will pass a AC current through this particular coil. So what is going to happen? Your AC current is always changing with respect to time. If that is the case, then naturally the magnetic field that it is producing is also going to change with respect to time. That means for the first half cycle, suppose the current is having a direction like this, then what will be the nature of the flux? So obviously for one half cycle, this one is going to behave as a north pole and this as south pole. In the other half cycle, this one, this is going to be your north pole and this is going to be your south pole. Number one. Number two, in case of DC, the magnitude was same, but here the magnitude is changing with respect to time in a sinusoidal manner. So naturally the strength of this north pole will start increasing from 0, reach a maximum position and then fall to 0. And after that it will change the polarity to south pole. So this is how the magnetic field is going to be alternating in nature when I am passing a AC current through the same coil. Now if this is the case, then I can say the fluxes that are produced around this is going to be alternating in nature. Now what I will do? I will take another coil and place it over here, just near to this coil. So if that is the case, now this flux is in the air, or it is near its vicinity. If I will place a coil, then this alternating flux is again going to pass through this coil. So if this is the thing, then obviously this is an alternating flux and it is passing through a new coil. Therefore, across it also there will be an induced EMF. So this is known as induced EMF or transformational EMF. In electrical engineering, we call it as transformer EMF. And the other one is known as motional EMF. Okay, so now it's already 57. I don't think I can be able to complete it. So in the next class, that is on Monday, Monday and Wednesday, by Wednesday we will complete this chapter. So then we will start with 30th chapter. So the next week and after that another week we have in our hand. So when are your exams going to start? 26th? Yes? 26 minus 14. That means we have 12 to 19. So we have another 2 weeks in our hand, right? So, okay, we'll try to complete it, and by chance if I can't complete, then chapter number 32, I will give you the slides, I will give you the notes, I will also give you that video clip so that you can learn it by yourself. Because after this, the most important thing, that is your AC circuit. AC circuit is very important, and Actually, you need to understand what is this AC circuit, how they are operating, what is happening, everything I will tell you in detail. Okay, so we'll stop our class over here. Is there anyone with any sort of doubt?
Sir, I have something to ask.
Yes, yes, please don't hesitate. Tell me
Why
loudly.
not? Why not permanent magnets are used in wind turbines? Not wind, but in substations or where there are
Okay,
bigger motors. Why permanent magnets are not used?
okay, let me tell you the main reason. Number one, permanent magnet. If you will go for a very good type of permanent magnet, okay, so let us say this is a permanent magnet, and in between this I am having a coil, and this coil is actually going to generate the voltage. Okay, number one, the problem with permanent magnet. Actually, I require a very strong magnetic field. Okay, so for that I require bulky magnets. Okay, so first thing, the cost is going to be very high for a good magnet with a good magnetic strength. Usually they will be made out of selenium, nickel and cobalt in combination with a few percentage of steel. So the alloy itself is a very very costly one. Number one. Number two, the weight is going to be too high. Weightage. First is cost. The second reason is the weight. Third thing, because of this, a lot of heat is going to be generated when this generator is going to be loaded completely. So obviously there is no relationship between the current carrying conductors and this magnet, but still then in the vicinity you have the coils, and these coils are getting too much heated up, and moreover the air gap between these two in the, believe me, you are seeing that the air gap over here is around 1 centimeter, but the truth is that in even in case of practical generator, the air gap is even less than 1 centimeter. Just imagine if this is the, so small is the air gap, just imagine how much heat will be produced, and that heat is decremental to the magnetic property of this magnet. This is the third problem. Fourth problem, you cannot have good control over the magnetic field because E is equal to. So when you will study, of course you will not study, maybe you will be having a paper on this electrical machines. So over there you will see that your voltage produced is directly proportional to the magnetic field strength. Now, sometimes what happen, we need it, because if we load the generator, there will be drop in the voltage. So when there is a drop in the voltage, so you want to increase the magnetic field. In case of permanent magnet, you cannot increase the magnetic field. That means there is no provision to change the value of the magnetic field strength. These are the main reasons, and the last one is the most important one. You don't have any provision to control the magnetic field strength of the generator. So instead of that, if you are using electromagnets over here, you are using electromagnets. Let us say we are having a electromagnet like this, and suppose I want to change the magnetic field, I will use resistance. So this was a old practice. Nowadays we are not using resistance, rather we are using thyristor. So you will not learn about all this thing. So there are semiconductor devices known as thyristor, in which actually we are controlling the current or the strength of the magnet by changing the resistance of the circuit. There is loss of power, and loss of power is like a crime to an electrical engineer. It is a crime for us. So naturally we will want to minimize the loss of power as much as possible. So nowadays we are actually making use of silicon control rectifier, that is known as thyristors, and we are changing some firing angle, and thereby we are changing the current through this field circuit. So by manipulating the field current through this means electromagnets, we can actually vary the value of this B, and thereby we can adjust the voltage. So this is the most important thing. Secondly, the coils, these are not going to lose their magnetism at all. How? Because once you switch off, it is not having any magnetism. Once you switch it on, it is going to gain the magnetism. So in that way, they are never bulky, and moreover, they are very they are having a very good economy. That means they are not at all very costly. So you obviously you will be using a good quality core. Now this core is much less in dimension in comparison to these permanent magnets. So these are the reasons why we are always, every electrical people, they will always prefer electromagnets rather than permanent magnets. Permanent magnet, their use are only limited to small equipments, toys, all these things. But nowadays, even Tesla has started using this permanent magnet because they are trying to maximize the torque using the least amount of energy. So that is a different issue. So research is going on. Let us forget about that. Got it?
That
Or is
is
there anything
something
else you want to ask?
reluctance motor, I think.
Yes? Yes, I cannot make out once again.
Synchronous reluctance motor. Uh,
Synchronous motor is
that
different. Reluctance.
is that a synchronous?
Synchronous motor. Okay. In case of synchronous motor, also we make use of electromagnets. Now, where you have heard this, I know, because there are two types of synchronous motors. One is a salient pole type, the other one is a non-salient pole type. And in both the cases, usually they consider the salient pole types to explain. But the truth is that salient pole types never also have permanent magnets. Every motor except the DC motor, saddle pole motors, and your reluctance motor, nobody actually uses a permanent magnet. Even in the past also, they are not using this permanent magnet for motors. Okay. The most important thing is that in permanent magnet, the magnetic field strength is fixed. You cannot change it. But electromagnet, you can change the magnetic field strength as per your wish. But of course, using electromagnet is not a very simple thing, because for that you have to have an elaborate control system like your SCR driving circuit, gate driving circuit, all these things. So quite a complicated one. Okay, by the way, somebody has actually chatted with me in the last session regarding this PID. So PID is actually proportional, integral, and derivative control. So it is a controller which is going to control some equipment, some signals. So if you want an elaborate discussion, we can discuss it sometimes, anytime. So that is not an issue. If you want to know, you have just written what is PID. So PID is proportional, integral, and derivative controller. So it is a controller which is going to control some signals. For example, let me give you an example. Suppose somebody is going to throw a hit a pendulum. The pendulum will first move to a very high distance. So this is the center. It will move to a high distance, then it will overshoot and come to this position. Again it will overshoot, like this, like this, like this. After a number of times, it will come back to its original position. Now, if I am, suppose the same thing is a electrical problem, then if we will use this PID controller, then the pendulum, you hit the pendulum hard, but after only one or two times, it will come back to this position. Without the PID controller, it is going to make these types of oscillation and settle down. Whereas using PID, you will get these types of oscillation. Only one or two oscillations, and it will be back to its equilibrium position. So this is the usual use of PID controllers. Anything else? Yes, any other thing you want to ask? Maybe outside, if you're inquisitive, you can ask. If I have the answer, I'll answer. Or we'll stop the class over here.
I have sent a video on your WhatsApp.
You have sent me
Please
a
check
video
that.
on WhatsApp. I
Uh,
cannot make out. Please repeat once
it's
again.
I sent you a video on WhatsApp
Huh?
and link actually YouTube which I saw,
Huh?
and I asking the same question.
Huh? Now, on what
So
subject the video was there?
That's a motor concept.
Motor concept. Okay, so you are trying to get some knowledge about motors. That's good, no problem. Now, basically, for what you are interested, if you want to, you can tell me. Then I will pinpointly give you some idea over that type of motor if I do have some idea. On what type of motor you actually want to know?
So in that video,
Huh?
the guy was saying that the Tesla car uses a synchronous reluctance motor,
That
and
is what I was telling you.
some permanent
Yeah,
that thing
I got
has
it. I
some
got it.
permanent magnets to increase its starting torque.
Okay, let me tell you. Actually, what is the problem with this regular motors? What Tesla is actually doing now? Tesla is a very means cunning company, and what he actually does is he uses all the advantages of the different motors and try to bring it to one motor. For example, there is something known as DC series motor which have a very high starting torque. So obviously, when something is going to start, suppose you are going to start a bike with two persons sitting behind you. Obviously, you have to push the accelerator a bit hard because you require a lot of torque. So starting torque is always high. For that purpose, the best motor is the DC series motor. So this is one advantage. So they will combine it to their motor. Why? Because if their car is completely loaded, it must start with a good torque. Now DC motor has a disadvantage, its speed regulation is very poor. That means if the load is high, the speed is very low. And if the load is light, then the speed is tremendously high. So this is the disadvantage. Now Tesla want to remove this disadvantage, but take only the advantage of good starting torque. So the motor which is going to have this property, that means good speed regulation, is the induction motor. Rather, I will say the slip ring induction motor. For that, they have actually in the previous model, before the S model, in the X model, they were actually using something known as induction motor, three-phase induction motor. But again, this induction motor has a problem. What is that? There is actually the speed of this induction motor is controlled by something known as voltage by frequency control. And over there, at high voltage and low frequency, the torque becomes very weak. So how to remove this one? For that, they felt that no, instead of going for a three-phase induction motor, let us do one thing, use the principle of three-phase induction motor and design the motor. That means here they are combining two things: the good property of DC series motor, the good property of your three-phase induction motor. So by that, they are almost, they have reached to a point where their motor was something like a BLDC motor. In BLDC motor, you have three phases, but these three phases are electronically created by means of DC signal. Obviously, they will be using a battery pack to run their motors. So in that case, again, there happened to be a small problem. The problem is that there is when you are trying to means bring out features in everything, some lacunas will always be there, and the lacuna was that they have actually adopted a design of motor in a DC concept, and they're using a AC concept to run it. The design is based on DC motors and the running is based on AC motors. So there lies the problem. So wanted to bridge this gap. So in order to bring this gap, they use something known as a COM pole. And this COM pole is nothing but a permanent magnet. So till this much I have understood. Beyond that, I don't have understood. So if you'll ask me their further
Why
development,
don't
I
they
cannot
use
explain.
gears?
Yes?
Why don't they use gears to increase the
Okay, let me
torque?
tell you. Okay, let me tell you what is the difference between a geared vehicle or a transmission system and without a transmission system. Now, in case of IC engines, you have a engine which is using the fossil fuel to develop the torque, or which is going to develop the mechanical force. Now, this if you have noticed, if you have traveled in a car which is equipped with a tachometer, tachometer is the one which is going to give you the reading of the engine RPM. You will see that the engine RPM is around 2000 RPM under the first or second gear. Okay. Now under this condition, just imagine if 2000 RPM is transmitted directly to your wheel, your speed will be around 100 kilometers per hour, and you just cannot control it. So what happens? The power from the engine is actually moves to the wheels through a elaborate system known as transmission system, which basically is a set of gears and clutch. Whether it is a manual transmission or an automatic transmission doesn't matter. Even in automatic transmission, you do have gears. The only thing is that you may not have a clutch, and the setting of these gears will be automatically done through some softwares. Okay. Now, in case of, let us talk about the manual model. In case of manual model, you set the first gear. The first gear is having a very large diameter. So naturally, maximum when the diameter is high, the speed is less. So this thing you have studied in your plus 2, conservation of angular momentum. So what happens? The engine RPM is now reduced because we are using a high gear, low gear with a higher diameter. So the RPM reduces to manageable unit, but the torque becomes high because angular momentum, conservation of angular momentum. Angular speed into the torque is actually constant. That means if the speed decreases, the torque will be high. That is the reason why at low gear, first gear, second gear, or in the reverse gear, you always get a very slow speed, but the torque is very high. It can pull the vehicle very easily. But at higher gears, let me tell you, at fourth gear or the fifth gear, or nowadays it is coming with the overdrive gear, sixth gear, over there, the speed is very high, but the pulling capacity is small. If you face a steep elevation on the hill, in the fourth, fifth gear, you cannot pull the vehicle with 5 passengers. You have to downshift to first or second. So this is the process. Now, in case of electric vehicle, actually what happens is that in case of IC engine, the engine RPM is always maintained at a constant. Why? Because if you will ask any automobile engineer, they will tell that we have something known as a RPM band or torque band. Within this RPM, the engine is going to produce the most efficiently it is going to run. It will going to consume less amount of fuel but generate an ample amount of torque and speed. So there is a particular range over which you can run the engine. Therefore, you require a gear system to change the RPM as well as torque. But in case of electric vehicles, we simply can control the speed, torque, everything on the motor itself by controlling or giving the signals. That means if I am using V by F control, that means by manipulating the ratio of the voltage to frequency, I can manipulate the torque and speed of the motor itself. So if I can control the speed of the motor directly and I will connect it to the wheels, then there is no problem. But the truth is that even in case of electric vehicles, whether it is by Tesla or whether it is by Mahindra or whether it is by Tata or whether it is by Audi, anywhere you will see their electric engine is also connected to the wheel by means of a transmission system. The only difference is that in IC engine, you may be having 5 number of gears, but in case of electrical vehicles, you have only one set of gear, only a single gear, which you don't require to change. Because if one is there, then why you will change? There is no need of changing, so no clutch arrangement. So naturally, the transmission system is eliminated, the weight of the vehicle is reduced, and moreover, the same performance is achieved. Got the idea? I got it or not?
Yes, sir.
So remember, transmission gear system is still there in means your electric vehicles, but it only has a single gear. And there is no meaning in using a gear system in this electric vehicles. Absolutely no need, because the use of the gear is done by controlling the parameters that you feed to the motors. You change the voltage, you will get a different speed, or you change the frequency, you will get a different speed. You change both of them, you will get the required amount of torque. So it doesn't matter at all. But in case of manual transmission, obviously, or IC engine, you have to change all this thing, the torque, the speed, all this thing you have to do by using the transmission system, whether it is automatic or a manual transmission. Any other doubt?
No, sir.
No,
Shall
sir.
we stop the class over here, or anything else you want to ask? So I hope everybody has all their doubts cleared. So today we'll stop it over here. Yes, anyone?
No, sir, all clear.
Okay, fine. So we'll stop it over here, and then the next week we'll try to complete this chapter as well as chapter 30. So that the last week will be only for 31 and 32. If by chance I miss 32, then I will give you all the materials for you all. Okay. So thank you all.
Thank you, sir.
Have a nice
Thank you, sir.
weekend.
Sir.
Okay. All of you have a nice weekend.
Thank you, sir.